Hi everybody. Hope everybody's having a good day today so far. Today we're going to talk about what I would call unifying some of the notions we've been dealing with. N-tuples, sequences, functions, and subsets. So we're going to be talking about n-tuples as functions. Then we will talk about sequences as functions. We'll talk about something called an indicator function or indicator functions, and we'll talk about the power set, which will be the collection of all the subsets of a given set. And we're going to see how these four different ideas are all related to one another. So in a sense, we'll be unifying these ideas in a certain respect. So let's get started. Let's start out by looking at elements of R2. So let's start with the kind of the simplest place here. Let's say if we have an element, an x in R2, a point or a vector in R2, then we could write that x is equal to x1, x2. Well, but notice that the fact that I wrote the 1 and the 2 as a subscripts, I mean, I could have written them instead as superscripts. I could write them this way. Whoop, whoop. I need to put the equal sign in there. We don't want to leave that part out. So I could rewrite this way. That would be okay too. Subscript, superscript, inside parentheses is like an argument of a function. And in fact, when I write it this way, we can see that each one of the x's in R2 really is, in a certain sense, a function, because it is a function that tells us for the number 1, what's the first component, a real number. And for the number 2, what's the second component, a real number. So actually, writing it this way makes it clear that each of the x's in here, each of the points in R2, is actually a function from the set consisting of just the first 2 numbers or indices into R. It tells us for 1, what's the first component, a real number. For 2, what's the second component, a real number. And actually, this is a function just as much as this is. It's just that it isn't written with the arguments in parentheses. It's written with the arguments as subscripts. What's the difference? Parentheses, subscripts. This is, of course, way more common. This is kind of the standard, the convention. And it's a little more economy of writing things. There's sort of more going on here, and it's not as obvious. So this is a little easier to work with. But conceptually, no difference. Well, I can do the same thing, of course, in Rn, and so I'm basically just going to rewrite what I have up here, and I'm just going to write it as x equals x1 to xn, or x equals x of 1 to x of n. So I have x as a function from the set of the first n natural numbers, the n possible indices here, again, into R. Well, next, let's look at sequences. So we've already said that we could write the set of all sequences, that's supposed to be infinity there. We could write the set of all sequences, we could denote it by R infinity, and so every one of these sequences is not really an n-tuple, of course. Looks like this, where this goes on for the indices keep on going. And let's even note that we could also write it as in the more standard notation, like this, with the curly braces. And of course, we could again write it this way. And writing it this way, again, makes it kind of clear that every x in here is a function from the set 1, 2, and all the way out, continuing to go on forever, all the natural numbers into R. And so, of course, I could rewrite this set as just n. X is a function from the natural numbers into R. And so in each case, our n-tuple, even if it's an ordered pair, it's an ordered n-tuple, ordered pair, and it's ordered partly because the terms are ordered by the order of the indices in the domain of the function that defines the ordered pair, the ordered n-tuple, or the sequence. And let me say as an aside, while this is the more standard way of writing it, people do write sequences this way. I will often write sequences this way instead of this way because this is confusing. This is kind of ambiguous because it gives us the same notation for an, I won't call it an n-tuple because it isn't just n, but it goes on like this. It's the same notation for the sequence, this function here, as for a set, the set of the terms. Those are different things as we will, well, as we've already seen back in the very first lecture in the course, and we will see it again concerning sequences and the sets of their terms, which are different things. So using the curly braces is actually ambiguous and confusing, but since it's so standard, we will sometimes use that notation. And we also use the notation like this as the name of the function, right, that goes from the natural numbers into R. And by the way, note that here, the curly braces, that is a sequence. Could just as well, and maybe better, use parentheses. Here, this is not a sequence. This is a set. There's the distinction. This is a set, the set of natural numbers, where things can't be repeated. Here, things could be repeated in the sequence. Remember, very first lecture, that in n-tuples, and by extension sequences, we can repeat terms. It could be a constant sequence. x1 equal x2 equal x3, they could all be the same. Here, this is a set. No repetition allowed. 1, 2, 3, keep on going. So the same notation of curly braces being used for two completely different things. Confusing, ambiguous. Now notice that it wouldn't have been, well actually first let me notice or let me remark that we could have written R2, it wouldn't be crazy to write R2 in a way that says the components are real numbers, but the elements, vectors if you like, made up of those components, they have an index from 1 and 2. And it wouldn't have been crazy to have written Rn this way. And it wouldn't have been crazy to have written the set of all sequences this way. Now I say it wouldn't be crazy, but of course this is kind of awkward and kind of not very clean. Same here, this is not so bad over here. But I just point out that we might have done that, and in fact we're going to do something like that in order to do this kind of unification that I talked about. Before going there, let's just write down a definition. We haven't actually given before a definition of a sequence. I've talked about how we could use the notation R infinity as a notation for the set of all real sequences, sequences of real numbers. But I didn't actually write down a definition of what is a sequence. I'm going to do that here. And of course, the definition is going to be just what we have here. So definition, and now I'm going to say not just a sequence of real numbers, but possibly a sequence of vectors, or a sequence of anything drawn where the terms are all drawn from some set X. So we'll say for any set X, for example, X could be R, for any set X, let's not say the, let's say a sequence. A sequence in X. So this is a definition. A sequence in the set X is just what we said up here. A sequence is a function except that it doesn't necessarily go to R. It goes to R here because R is playing the role of X. But in general, this is going to have to match up here. So this should have been a capital X. And so this is yet another instance where we have a definition or a theorem, in this case a definition, of a term, a sequence, the notion of a sequence, and then we apply that to real numbers. A sequence of real numbers, a sequence in R, is a function from the set of natural numbers into R. R here is playing the role of X. So we just see this all the time, over and over. We're seeing where we apply some definition or theorem to a specific case, and then we have something in the specific case playing the role of the items in the definition or the theorem. But notice that even in the finite case, where we're looking at n-tuples, where n is a finite number, it wouldn't have been crazy. It would really be perfectly okay to refer to the n-tuples and the ordered pairs, specific kind of n-tuples, as finite sequences. Sequences defined not over an infinite set, but over a finite set, here and here. It'd be perfectly sensible, and in fact, occasionally you see people do that, refer to these as finite sequences, but I think that's pretty unusual because we tend to reserve the term sequence for sequences that go on indefinitely, that have an infinite number of terms, that is, sequences that really are functions defined on the natural numbers, not defined on a finite set. But this is just to point out that all it is an extension of the notion of n-tuples here. They could be regarded as finite sequences. So this idea that I posed here, where we could have written R2 by using the set, that's the domain for the function defining the elements of R2, or we could have used the set 1 to n, the domain of the function that defines an n-tuple. And here, where we used the set of natural numbers, the domain for our function that defines a sequence, I'm going to use that as a kind of motivation for a notation that we use. So let's put that over here. So here we have a notation, and that is going to be that for any sets X and Y, the set of all the functions that map from X to Y well, before I write down how we denote that, let's look back here. Here, a sequence is a function from the natural numbers into the set where the terms of the sequence live. So for example, for sequences of real numbers, every one of the sequences is a function from here to here. So the set of all of the sequences, we write it this way, or we could write it this way. This is the set of all functions, set of all sequences. It's the set of all functions from n into R. And I said we could have written the same thing here for the set of all functions from this set here into R. And we could have written this, if we wanted to, as the set of all functions from here into R. And so, as I said, this motivates the definition of this notation here, which is going to be y, and we write it as if it's y to the x power. Now these aren't numbers in general, because these can be infinite sets, as they are, if either y or x is R. So this isn't really the power, isn't this number to this power. It is just a notation for the set of functions from this set into this set. Okay, and a second piece of notation here. That is for sets that are finite. For finite sets X, we use something that looks like the absolute value, but it's not the absolute value because it's not a number, that's a set. We use this notation here. We use this notation here for the number of elements in X. Which, of course, because X is finite, is perfectly well defined. If X was the real numbers, then there is the number of elements of the set of real numbers doesn't have any real meaning. So we can talk about its cardinality as something like the number of elements, but here we want to have something that's kind of explicit and clean. And so if we have a finite set, we can talk about the number of elements in it. That denotes the number of elements. And then let's say as a remark, if X and Y are both finite sets, then we can say something about this notation. That is that the set of functions from X into Y, remember they're both finite sets, the set of functions going from X into Y, the number of such functions again, these are sets, not numbers, and this is not the absolute value. This is the number of elements in the set. So the number of functions from X to Y is the number of elements. So this is a number. The number, that's a set. This is a number. It's the number of elements in the set Y raised to the power. So here it really is a power. This is an integer. That's an integer, natural numbers, raised to this power. So let's say, let's even put in parentheses, if the number of things in X is n, and the number of things in Y is m, then what this says is that the number of things, the number of functions that go from X to Y is m to the n power. Now I'd like to give an example here. Let's do an example where, in fact, I think we can take this off and we'll do the example over here. So let's take this off and we have a little more room. This is getting a little congested down here. So let's take this off and we'll do our example over here.